Hi, we're B3 and this is our project AnomAIy. We built a predictive maintenance monitoring system for liquid-cooled servers that detects developing hardware degradation, both in the cooling loop and in the power delivery circuitry. Data centers support essential services like banking, medical records, and cloud platforms, so server uptime is critical. Cooling is a major part of that reliability. Liquid cooling is becoming more common because it removes heat more efficiently than air, but it also introduces new reliability issues. In particular, we focused on two realistic degradation modes. The first is flow restriction. Over time, minerals and additives in the coolant can leave deposits inside the loop, which gradually restricts flow and reduces the loop's ability to dissipate heat. The second is VRM phase degradation. Modern CPUs use multi-phase voltage regulators. If one phase starts to weaken, the remaining phases have to carry more current. That extra load creates additional heat and stress, which can eventually cause the VRM to shut down, cutting power to the CPU and crashing the server. Both of these faults begin with very subtle temperature and power deviations that fixed temperature alarms usually don't catch. Detecting them early requires an ML-based predictive maintenance approach, one that learns the system's normal behavior and flags when that behavior starts to drift. Our system monitors temperatures, pump and fan speeds, and CPU power. It learns how the system normally behaves and raises an anomaly when it detects a hardware fault. To detect anomalies accurately, our monitoring model has three stages. First, it predicts what the CPU power should be based on temperatures and the pump and fan speeds. Then it looks at the difference between expected and actual behavior over time. An autoencoder analyzes those patterns and outputs an anomaly score. And when something looks off, a classifier determines whether it matches a flow restriction or a power delivery issue. Once the anomaly score crosses a threshold, the system sends an alert in the Pi terminal with the type of fault. To evaluate the monitoring system, we needed controlled examples of both types of degradation. We can't intentionally damage a real server to collect this fault data, so we built a small liquid cooling loop using typical components found in a real server: a pump, fan, radiator, and CPU water block. We used power resistors to simulate the CPU and VRM, and we placed temperature sensors throughout the loop. This gives us realistic data while letting us safely induce controlled cooling faults. A Raspberry Pi 5 handles data collection and runs the ML models, and a Pico controls the hardware, adjusting CPU power and inducing faults based on commands from the Pi. Together, this setup lets us generate realistic training and test data and evaluate the detection pipeline end to end.
To run the test platform safely and reliably, we split the control tasks between the Raspberry Pi and the Pico. The Pi handles all of the higher level work, including collecting sensor data, storing it, and running the ML model. The Pico is dedicated entirely to hardware actuation. It drives the SSRs that control our power resistor, generates PWM signals for the pump and fan, and adjusts the servo valve. The Pi sends commands to the Pico over UART with what to set everything at. We added a heartbeat signal so that if the Pi ever stalls during data collection or model inference, the Pico automatically shuts off power to the resistors to keep the system safe. The setup gives us reliable control over the two mechanisms we use to induce faults: adjusting the servo valve to restrict flow and increasing VRM equivalent power to simulate efficiency loss.
To train and validate our monitoring model, we collected data from the sensors on our testbed during the normal runs and during both fault scenarios. We used 3 temperature sensors, one in the coolant reservoir and 2 placed across the radiator to measure the difference in inlet and outlet air. We also record the pump and fan tachometer signals, since changes in their speeds affect how quickly heat moves through the system. During every run, we log the power going to the CPU and VRM resistors, so the model can learn what power conditions produced each temperature pattern. All of this data is streamed into an Influx database, which lets us watch what's happening in Grafana as it runs and also exports complete runs for training.
Next, we'll demo the model running on our testbed. Here, the system is running under normal conditions. We vary the resistor power to simulate CPU spikes and different workloads, which creates small changes in temperature and total power. On the dashboard, you can see that the temperature is increasing with the power load. During these runs, the anomaly flag stays at 0 and the anomaly score remains low below the threshold, which confirms that the model isn't giving false alarms when the system is behaving normally.
Then, we simulate a power delivery fault. In real servers, this happens when a VRM becomes less efficient and wastes more power as heat. On our testbed, we recreate that by increasing the amount of power going to the VRM resistor. You can see on the CPU and VRM power graph that the VRM power line becomes a noticeably larger share of the total power on the dashboard. The system shows a slightly larger temperature rise for the same CPU power compared to the other runs. In the terminal, the system flags the anomaly and correctly labels it as a power-related fault.
Finally, we simulated a flow restriction fault by partially closing the servo valve, which reduces the flow rate through the cooling loop. The temperature and power still look very similar to the normal run, but the underlying relationship between them shifts as the reduced flow rate affects how heat is dissipated. The anomaly score rises and eventually crosses the threshold. In the terminal, you can see that the system raises an alert and labels the issue as flow-related.
Across different workloads and ambient conditions, the model consistently separated normal behavior, flow-related issues, and power-related faults into distinct groups. The important takeaway is that these groups separate very clearly. That means the model isn't just memorizing data, it's learning the underlying patterns that distinguish each fault.
One of our biggest challenges was getting the ML model to clearly separate normal behavior from the two fault cases. The differences are very subtle, so achieving clean separation took a lot of iteration and careful feature design. We also ran into new challenges when we moved from offline training to live monitoring. Some features that worked well during training weren't practical to compute in real time, so we had to rethink parts of the pipeline and simplify how we process data.
Thanks for watching. This is AnomAIy, our ML-based predictive maintenance system for detecting subtle cooling and power delivery faults in liquid-cooled setups.